Hey guys, so welcome back to part three of our random variables discussion. Today we're going to look a little bit more closely on how we deal with the normal model when we're talking about this idea of combining random variables. So let's get started. So we're just going to go straight into some examples where we are combining random variables, but also doing some stuff with the normal model. So our first example is about SAT scores. A college uses SAT scores as one of the criterion for admission, obviously. Experience has shown that the distribution of scores among its entire population of applicants is shown in this lovely table. So we have the math score, mean and standard deviation, and the verbal or reading score, mean and standard deviation. So then our first question is, what are the mean and standard deviation of the total SAT score? So the combined SAT score among students applying to this college. So basically I would be adding together the math score plus the verbal score for each student. And I want to know what would be the mean and standard deviation of all of those combined scores. So our mean, otherwise known as our expected value, so expected value or mean of math plus verbal. Well, our combining rule when we're just adding two variables, expected value always does what you expect it to. So I'm basically just going to add the means. So 625 plus 590, which is 1215. And then for standard deviation, we have that whole rule or trick that we can't just add standard deviations. We have to add variances and then work back to standard deviation by taking the square root. I kind of call this the Pythagorean theorem of statistics. So the standard deviation of math plus verbal would be square root of math standard deviation squared plus verbal standard deviation squared, which comes out to 134.54. However, in order for that to be the combined standard deviation, remember we had this rule when we're combining two different variables or more than one variable in terms of variance or standard deviation, so we have to know that the two variables are independent. And in this case, they probably aren't. Someone's math score is not necessarily going to be independent of their verbal score. If they're a good test taker in general, then both will probably be relatively high. If they're not a good test taker, if their math score is lower, their verbal score is likely going to be also lower as well. Or there might be somebody who's really good at math and not as much at verbal. But either way, that those two things, because it's being taken by the same student, they do affect each other. So because they're not independent, it would not be appropriate to find that combined standard deviation because we don't know how the standard deviation is going to change based on that dependency. So we cannot calculate it with this information, unfortunately. So because we couldn't do the standard deviation, there's not a whole lot else we could do with that problem. So we're going to move on to example 2, which is about bikes. So bicycles arrive at a bike shop in boxes. This means that the means and standard deviations for the setup phases are given in the table below in minutes. So we have the unpacking phase, the assembly phase, and then the tuning phase of a bike. So a customer decides to buy a bike like one of the display models, but wants a different color. The shop has one in that color, but it's still in the box. So the manager says they can have it ready in half an hour or 30 minutes. And we're going to find the probability that they can get the bike set up and ready to go in that promised amount of time. So 30 minutes or less, right? If they did it in less than 30 minutes, he's still keeping his promise. So we're trying to figure out the probability the combined time for unpacking, assembly, and tuning can happen in 30 minutes or less. That's kind of our goal. There's two things that we are told in addition to this. Based on past experience, the shop manager makes the following assumptions: that the times for the 3 setup phases are independent. That's important because if we're going to do any kind of combining and need the standard deviation, which we will need in order to find this probability, we need to know that the 3 phases are independent. So maybe they're being done by 3 different teams or crews or whatever. The second thing is that the times for each phase are approximately normally distributed, which is going to allow us to use the normal model to find our probability here in a couple of minutes. But our first step, before we can even get into normal model, is we have to know the mean and standard deviation for that combined time. I need to combine the 3 times into one kind of normal model with a mean and standard deviation. So, right, our first step is to find the mean and standard deviation of the combined setup time. So for mean, or the expected value of unpacking plus assembly plus tuning, Remember, expected value always does what you expect it to, so I'm literally just going to add the 3 means and get 38.6 minutes. Easy cheesy. Standard deviation is tricky and annoying in that we can't just add standard deviations from 3 different variables. I have to add their variances and then square root. So standard deviation of u plus a plus t would be the square root of 0.7 squared plus 2.4 squared plus 2.7 squared. So we square each standard deviation to get their variances, combine the variances, and then square root it to get back to standard deviation, which is 3.68 minutes. So that's our first step. Now that we have this mean for the combined time and a standard deviation for the combined time, we knew that each individual phase times were normally distributed, which does also mean that the combined time is also going to be normally distributed. So now we're ready to go ahead and use our normal model to find that probability that the combined time is less than or equal to 30 minutes. So way back to normal model stuff, in order to do that, I need to find a z-score. I need to know how far away is 30 minutes from that mean of 38.6 minutes in terms of standard deviation. I need to know how far away those two values are. So I'm going to find my z-score. Z-score is observed value, which in this case is 30 minutes. That's what we're finding the probability for, minus our mean combined time of 38.6 minutes, divided by our standard deviation 3.68, which gives me a z-score of negative 2.34. So I'm going to draw my normal model. 38.6 is our mean that goes right in the middle. The time that we are finding the probability for is 30, which is obviously less than, and we just found out it's 2.34 standard deviations less than, so it's pretty far down there. And then we are finding the probability that our combined time is less than 30 minutes, or the probability that our z-score is less than negative 2.34. So we would shade to the left on our lovely little normal model there. Now, in terms of finding that probability, go find your z-table from way back when. It's still under resources in Schoology. If you don't have it anymore, if you do have access to a printer, I would definitely encourage you to print it because it'll make your life a little easier. In class next time, I will show you, if you remind me, how to do this on the calculator. It's good stuff. But if I look on my z-table, I'm going to get a probability of 0.0096. And since we wanted the less than probability, we know that's our final answer because that's what our z-table always gives us, is the less than probability. So that is our answer. There is a 0.0096 probability or a 0.96% chance, less than a 1% chance that they can get the bike ready to go in under 30 minutes. So the manager is definitely promising more than he should. Let's do another example. We're going to talk about a basketball tournament. So every spring at good old Podunk High School, the basketball team hosts a basketball tournament as a fundraiser. For this tournament, junior and senior contestants are randomly paired up as teams, and the means and standard deviations for the heights of the players are given below. So we have the mean height for juniors and the standard deviation, and then the mean height for seniors and the standard deviation, for at least the ones that are participating. And we're going to assume that the heights of juniors and seniors are independent of each other, which is a pretty good assumption, and that both distributions are normally distributed. So we need the independent in order to do any kind of combined standard deviation, and then we need the normally distributed so that I can use the normal model to find a probability, which I will need. So this part A question is going to ask us to find the probability that a junior contestant is paired with a shorter senior contestant. So we're finding the probability that the junior is taller than the senior. And according to our means and standard deviations, that doesn't seem incredibly likely because our mean for juniors is less than our mean for seniors, but it could happen, right? So again, our first goal is to find our combined standard deviation and mean. But for this one, I don't want the addition. I don't want the sum of these numbers. I want the difference. I want to know how much taller is the junior than the senior, or vice versa. So I'm not interested in a sum or a combination. I'm interested in the difference. So I would be finding the mean and standard deviation of the difference in their heights. Now, in terms of which way you subtract, you could do it either way. You could do juniors minus seniors or seniors minus juniors, whichever you felt like. They're both a difference. That would just affect what probability we're finding later. So I'll explain that when we get to it. But just to make things easier, because I don't like negative numbers, I'm going to find the difference in, hello, there we go, seniors minus juniors, because seniors mean is higher than juniors mean. So my mean, or expected value, always does what I would expect it to. So I'm just going to subtract the two means. 68.5 minus 656 is 2.5 inches. And then for standard deviation, we can't just add standard deviations or even subtract. We have to deal with variances. And then this will also go back to what we talked about last lesson, in that variance always increases when we're doing any kind of combining. So even though we're subtracting the variables, we're going to add the variances. And you can go back to lesson 6b and watch that little piece to remember why we do that. So the standard deviation of seniors minus juniors heights would be square root of 1.8 squared plus 2.2 squared, which is 2.843 inches. So that is our mean and standard deviation of the difference in the heights between juniors and seniors. So now we can continue on and find the probability that the junior is taller than the senior. So again, what I found the mean and standard deviation for was senior minus junior. So I kind of have to think about, right, if I want the senior to be shorter than the junior, I want S to be less than J, then I want S minus J, which is what I found that combined mean and standard deviation for, to be less than 0. If S is less than J, then S minus J will be a negative number, or less than 0. Now I have to put it in terms of the mean and standard deviation combined that I found. So since I found that mean and standard deviation for S minus J, that's what I'm kind of thinking about in terms of my probability model. Now, if I had found the mean and standard deviation for J minus S, junior minus senior, then I would be finding what's the probability that J minus S is greater than 0, that the junior is taller than the senior. So you can do it either way. It's just based on what you actually did in your combination step. So now that I've figured out what I want to find, we're going to set up our normal model and find our z-score. Our observed value here would be 0, because I'm finding the probability that S minus J is less than 0. So 0 is my observed value, minus 2.5 was the mean of the differences, divided by 2.843 was the standard deviation of the differences, which comes out to negative 0.88, so a little bit under 1 standard deviation below the mean. So I'm going to go ahead and draw that. Again, 2.5 was the mean difference, and then 0 is the observed value that I'm finding. I want to know if there's a difference of 0 or less. So my probability that I'm finding that S minus J is less than 0 is like finding probability that our z-score is less than negative 0.88. So I'm going to shade to the left on my little normal model. And then again, I would look it up on my z-table, find that negative 0.88 z-score, and then find our probability. Okay. I said I would do it next class, but I'm going to go ahead and show you just real quick, if my mouse wants to work. There we go. How I would do this on the calculator, just as another option. You can still always use the z-score or the z-table. It's always there. But just real quick, if I go to second, and then this VARs button that's kind of under the arrow, it says distr above it, which means distributions. So that brings me to this list. I'm going to go down to Normalcdf, which is number 2. Okay. The lower I'm going to keep is that. That's just basically a super negative number. It's what'll allow me to do less than. For the upper, I'm going to put my z-score, so negative 0.88. And then I'm going to leave those the same. And that's all I'm going to do. So I'm just changing that upper to my z-score. And I'm going to hit paste and then enter. And it gives me that probability that I got from my z-table. There are a lot of other ways I can use that Normalcdf function, but for your sake, at least right now, if you want to start using the calculator, I would just always use it in this way. Only change upper to your z-score, leave everything else the same, and then it basically does exactly what the z-table does for you. Okay. If you do have an older calculator that doesn't bring up that menu, you're basically going to have to type this in the parentheses. It'll just give you the Normalcdf parentheses, and you have to type in, -1, second comma gives you that E, 99, comma, negative 0.88. You don't have to do the 0, 1 part, but you would have to type that in after normal CDF and then push enter, just so you know. All right, so that's a little bit of a calculator trick. So that's our answer, 0.1894. There's a 0.1894 probability that a junior contestant would be randomly paired with a shorter senior contestant, or about an 18.94, a little under 19% chance that the junior would be taller than their senior partner. And then part B, based on the same example, just to do one more practice, find the probability that a senior contestant is at least 6 inches taller than their junior partner. So this time, instead of finding if the junior will be taller than the senior, we want to know what's the probability that the senior would be at least 6 inches taller. Again, it's not, the norm, because in our means, the senior is on average only 2.5 inches taller. So we're going to find what's the probability that just by chance we would get a senior that's at least 6 inches taller. The nice thing is that we've already found the mean and standard deviation for S minus J. So I don't want to have to redo work. So I'm just going to use that. So this would be finding the probability that S minus J is greater than 6, because that would mean the senior is at least 6 inches taller than the junior. So my z-score, my observed value would be 6 minus the mean divided by standard deviation, which is positive 1.23. So there was my mean of 5. Here's my 6. I want to find greater than that. So I'm going to shade to the right because I want to find at least 6 inches taller, which means 6 inches taller or more. So I'm shading to the right. And then again, I would look up on my z-table that 1.23. Because I want a greater than probability this time, I would need to find that number from the z-table. So our z-table probability is 0.8907, and then I would do 1 minus that since I want greater than, so 0.1093. On your calculator, the nice thing about the calculator is that you do have the option of doing a greater than, and how you would change that is I would put my z-score as my lower, so 1.23, and then for upper I would put positive 1 E99, and then I'm still going to keep the mean and standard deviation the same, and then that would give me immediately the greater than probability. Again, if you don't have the fancy menu, you would just type in 1.23 comma 1 E99. So that's just a little trick. The 0 and 1 don't matter. We're not going to change those, at least not right now. So that is my answer. There's about a 10.93% chance or 0.1093 chance that a senior would be at least 6 inches taller than the junior they are paired with. And that is how we connect our combination of random variables to the normal model. All right, see you guys in class.